see special Lorentz group in 2 dimensions with complex parameters, those Mn matrices. Okay, so we have identified 2 types of Sipners, zeta and eta. Okay, so this zeta transforms under Lorentz transformation as zeta prime as anybody, that m zeta, and this eta transforms as some eta prime like this in n eta, while m and n, they are not unitarily equivalent, or they are inequivalent to each other. Clear? So this we have shown. Now what is the form of this m? Anybody? M is equal to e raised for I sigma dot, okay, sigma by 2 theta minus I phi, probably. Clear? And then you are having this m is equal to e raised for I sigma by 2 dot theta plus I phi. And we have shown that this m star, this x operator, x on this side, that's equal to n, while this x is equal to minus I sigma 1. So they are related by time reversal operation. Clear? So this is what we have done in the previous lecture. Now let's move a little bit beyond. Clear? Okay. So and one more point, we have identified 2 types of Sipners. So you are having this zeta and eta. There are 2 types of Sipners. What kind of Sipners they are? So this is half 0, and this kind of Sipner is what? 0 half. You remember? In other words, we identified these 2 Sipners, J0, where J is the angular momentum of the particle, and 0 J. Clear? So these are the 2 types of Sipners we are having at hand. J0 belongs to this A and 0J belongs to this B. Clear? So these were the special cases we have identified. In other words, we have identified this representation under which any state you can label by definite angular momentum as a quantum number, J and J prime. Clear? So this we have done in the last lecture. Okay, so now let's take the parity. Although we will be taking discrete symmetries later on in this very course, I mean all the discrete symmetries, but we will see what is the effect of this parity on this Lorentz group. Clear? Samashaman? So, okay, so look here. So I have not considered here any kind of parity, only Lorentz transformation, Lorentz group transformation, and we have identified eta and zeta. They are 2 irreducible representations of what? This Lorentz group, because this zeta and eta, they both belong to this SU2, SU2. Clear? Now if I make now let me put in place a parity. In addition to Lorentz group or the Lorentz transformation, I am making use of parity. Now what this parity will do? Clear? So first let's define this parity. Parity simply means a coordinate transformation like this thing, a discrete coordinate transformation. Suppose I am given a vector x, okay, under parity, this vector will change to what? Minus x. It will simply change, it is simply a reflection about origin. Clear? So it's a mirror reflection. Got my point? So think about this as, okay, so it's a discrete transformation. Okay, because you cannot change continuously your coordinates in such a way you will get to this point. Clear? Samajh? There is a difference between discrete and continuous. Clear? So 1, 2, 3, 4, these are the discrete in sense. So you move in steps. Clear? Okay, but if you count infinite numbers, so it's a continuous kind of thing. Okay, so how many elements are there in this very transformation? There is only one. Clear? So what is that? So let's say if you are having this, let me write x prime, y prime and z prime. How it will go to minus x? So you multiply by minus 1, 0, 0, 0, minus 1, 0, 0, minus 1. Clear? So it's x, y and z. So that means you are having only one element which will make this x to minus x. Clear? Samashyaman? Or if you apply now again the parity transfer, it will take it back. So now apply again the parity transformation. What will happen? So under P, so what will happen? It will be minus x. So what you will get? X square. Clear? So okay. So now what happens under this transformation? So because I require these things, okay. So let's say your x goes to minus x under parity. Under parity P. Clear? So what happens to the velocity? What will happen to the velocity? It will change. What is velocity? Dx by dt, is it? So what will happen to velocity? So it will change the sign under parity. Clear? So now what will happen to the angular momentum? The J will remain unchanged because J is R cross P. Okay? So R changes, R goes to minus R, P goes to minus P. Okay? So that means J, okay, so we call this as a axial or pseudo vector. Clear? Got it? Okay. Now, if okay, now here under parity the angular momentum remains same. Clear? Okay. So now if my velocity changes, now on which parameter the Lorentz transformation depend? No. On which parameter? It is only velocity. Clear? So if you remember, in Lorentz transformation we define this beta is equal to V by C. That's actually this tan hyperbolic phi. Clear? Last time we have defined this kind of thing. Okay, now if V changes to minus V, what will happen to this phi? What will happen to this phi? It will change. Clear? Then what will happen to the boosters? In other words, what about the generators of the boost? So it implies therefore generators of the boost will also change SI. There will be a sign change. Generators of the rotation will not make any change. Okay, they will be invariant under parity, but the generators of the boost will be changing. Clear? So there will be a sign change. So everybody followed it? Okay, now look here. So how we calculate? Let's say you are having the boost matrix along x direction. What is that? Cos hyperbolic phi minus sin hyperbolic phi 0, 0. Is it? Then minus sin hyperbolic phi cos hyperbolic phi 0, 0. 0, 0. Sorry, I should. Okay, so it's okay. Clear? So this is the what? This is a boost matrix. Clear? Bx we wrote last time. Boost matrix along x direction. And then we define it. Now tell me what is the generator? So it is 1 divided by I partial bx by partial phi. Phi is the parameter. And phi goes to 0. So much sure? Now tell me, under parity, what will happen to phi? So under parity, phi goes to minus phi. Why? Because V goes to minus V. So much if V goes to minus V, it means what should happen to phi? It should change the sign. What will happen to this thing? This will remain as such. Clear? So what will happen to this thing? It will become plus. So this will become plus. This will become. It will remain as such because cos hyperbolic it's an even function. So much now what will happen to the boost generator? So because there is a sign change on these two elements, there will be a sign change overall. Clear? So in other words, this kx will go to minus kx under parity. Clear? Samajh aaye? Okay, so if you have understood it, now, okay, shall I rub it? Okay. So therefore, okay, so we have this kind of situation now. Okay. Now let me take this very generator. A is equal to half a j plus ik. Clear? Now let's apply the parity on this very generator. What will happen to this generator? Tell me. J will remain as such. K will change. So it is half a j minus ik. So what is that equal to? B. Now let's look at the B. So B is half a j minus ik. Under parity, what will happen? So it will become j plus ik. So that means A will go into B and B will go into A under parity. So there, what it implies, there is a connection between the two. So they are interrelated to each other, is it? Under parity. Without parity, they are not related. They are completely independent. So if I am considering now the parity, so they are related to each other. Clear? And how it is reflected? Now look at how they are reflected. Now for this A, okay, I am having this very vector or this very state. Okay, so this belongs to which sector? It belongs to A, is it? Okay. So now what this belongs to B. Clear? Samajh? Okay. So now what will happen? Now since A and B get interchanged, what will happen then under parity? That means under parity J0 goes to 0J. Samajh? So in other words, they are flipped. Under parity, what they are? The state vectors get flipped. Think of, let's say you are having a spin up state. Okay, you are having up spin and you make a parity transfer, what will happen? It will go to a down state. Samajh? Okay. So in other words, the representations are interchanged. Clear? So what it implies? It implies if I am considering parity, okay, if I am considering the Lorentz group with parity, then I need to consider a bigger state vector than the two component vector. Clear? Since this was a two component vector, look here. So you are having half and 0, is it? So it's a two spinner. Without parity, I am simply considering a two spinner. That means spin half particle. Clear? So now if I am considering the parity, okay, I mean if I am considering the Lorentz group with parity, then I need to consider a bigger spinner, is it? Summation of the components of which are related. Clear? So how, what is that bigger spinner? So simplest of the case, so let's take, if I am taking this half and 0, so since they get interchanged under parity, is it? So it means I need to take a 4 spinner instead of 2 spinner. So this should give you actually an idea why we require actually 4 spinner in Dirac equation. Is it? So we are going to see that. Yeah, Saran Samaj? Everybody followed it? So that means if I am considering the parity, okay, then A and B does not form the irreducible representation of the Lorentz group. Clear? Or in other words, these zeta and eta are not irreducible representation, okay, under Lorentz group. Clear? So I need to consider a 4 spinner. That will be the irreducible. So irreducible. Okay. So since we have reduced this to SU2, and we have shown A and B commute, that means there is no relation between this set and this set. Clear? So they are completely distinct to each other. But when I am considering the parity and I see the state from here, it gets, converted to this state, and state from here, it gets projected here. Clear? They get interchanged. You got my point? So that means if the states are, interrelated in these two branches, in these two sets, two SU2s, so it means, so it does not form now an irreducible representation. I need to figure out a different kind of irreducible representation of this Lorentz group. Clear? Or in other words, a state which corresponds to the irreducible representation. Okay. So for that matter, what I will consider, okay. So you can see, okay. So what I will do, let me write some psi is equal to this zeta and eta. Okay. So now this will be an irreducible representation. Okay. Clear? Or it may, okay. So you can consider any state vector which will transform under Lorentz group, extended by parity, will be a 4 spinner. Let's consider a 4 spinner now. Is it? The components of this very spinner are interrelated by parity. Okay. समझ आया? If you don't consider the parity, then zeta is independent of eta, eta is independent of zeta. Clear? So then you need to consider only two component stiffener or two stiffener simply. Okay? Now how they transform? So therefore, okay, so under Lorentz rule, so this psi, so let me write, so this zeta, eta, it transforms as like this thing. Okay? So it is e raised for the timing I am just writing under SU2, so it will be I sigma by 2 theta minus I phi 0, okay, 0 e raised power I sigma by 2 theta plus I phi, okay, zeta eta. Sorry, I should put a prime here. Clear? So this is how they transform under Lorentz transformations. Okay. So now let's use now the this extended psi. Okay. Now let's try to figure out what is the relation. So we have figured out there is a connection between the two stiffeners zeta and eta under parity. Okay. So now let's consider that kind of. Let's figure out what is the transformation rule that connects these two types of stiffeners. Samajh? Okay. So if you have any question, just tell me. Any question or any misunderstanding somewhere? Any confusion? Okay. So what I will do, instead of writing this zeta and eta, I will relabel them. Okay, this way. Let me define a kind of objective. Let me write phi r. R means right stiffener. Okay. So let me, since I am having how many stiffeners here? Two stiffeners, zeta and eta. Let me call one stiffener as a right stiffener. Samajh? No, it's not the bowler. Okay. So let's write this phi r to be what? This zeta. And let's define another stiffener, left stiffener, as eta. So you will come to know what exactly it means. So we will be having always these two types of stiffeners at hand. Okay. So you will be having the way you are having spin up state and spin down state. Clear? So we can define if we are having two types of particles, let's say. Clear? So now if you see how many components this zeta have? Two components. So let's think this zeta represents one type of particle. This eta will represent another type of particle. Clear? So now let's write a stiffener corresponding to one type of particle. Let's call it as a right stiffener. And for another type of particle, let's call it as left stiffener. Clear? Although they will be okay. And if I am taking the particles at rest, let's say massive particles, particles with mass. If I am taking them to be at rest, then we cannot distinguish between whether it's a left stiffener or right stiffener. Okay. Now let me put this way. How we define the spin of a particle? Okay. How we define the spin of a particle? No, just simple definition. I don't mean. So I am saying particle is a spin half particle. Or let's do this way. Let's define the helicity of the particle. So how you define the helicity of the particle? So you will just measure the momentum. Okay, projection of what? Spin along the direction of the momentum or opposite to that. So you will be getting two states. So let's say if you are for a particle, let's think of an antiparticle. Okay, so those things will be opposite to that. So what I have to say? I forgot. I forgot what I have to say. Okay, so I forgot. So let me come to this very point. In the meantime, maybe I may recall things. What I have to say? Okay, so let me continue from here. So then I will take. So what I am saying, I am having now two Okay, so this zeta represents spin half particle, eta represents spin half particles. I mean, I am having two types of particles here, right moving particle and left moving particle. Let's think them in this way. But if they are at rest, let's say, I cannot distinguish between whether it is right or left. So they are identical to each other. So let's remember this kind of rule. Okay. So now let me make a Lorentz boost along certain direction. Clear? So through an arbitrary direction on this very signal as well as on this signal. Let's forget about rotation for the time being. Let's make only the boost. Clear? So how I will do the boost? Okay, so let's boost phi r and phi l, okay, along arbitrary direction. What does that mean? Can anyone tell me? So that means I have to apply this object, is it? This transformation, since this represents rotation as well as what? Boost. Theta is a rotation parameter, is it? So since I am applying only the boost, it means theta is equal to 0. Got my point? So this will act on this zeta and this will act on eta. In other words, I will be having like this thing. So if I am taking this thing, so theta is equal to 0 here. So it is equal to e raised power. Now tell me, so it will be simply sigma dot phi by 2 acting on, what is zeta? So it is actually, so let me write zeta. So I will be having zeta prime, clear, for the time being. So what is zeta prime? What is this zeta? It is phi r. So, okay. So let's say it is at some rest, clear? Phi r 0 means it is at some rest. Now I am giving it a speed. Okay, now I am making the particle to move. So that is this kind of object, e raised power sigma dot phi by 2. So what it will be? It will carry now some momentum p. Okay, so I will write p. It is a 4 momentum p. Clear? So boosting means what? So you give it the energy, it will move with certain velocity. Clear? That means it will move with certain momentum. Now let's try. So what is this e raised power I phi? So it will be simply cos hyperbolic phi by 2 plus sigma dot n. Anybody? Or sigma dot phi? Then sine hyperbolic phi by 2 is it? Is it clear or not? Okay. Oh yeah, home Latin. Then we are having only, we had last time e raised power I, is it? So if it is I, then it will be cos instead of sine. So sorry, instead of cos hyperbolic. So is it clear? So just expand this by Taylor series expansion, you will get this very formula. Okay? Okay. Everybody followed it? Okay, so now let's rewrite this very equation. Okay, I am going slowly here because you need to understand what we are trying to do. So using these formulas last time, so we have written, what is the gamma we have written? Cos hyperbolic phi, clear? Then we wrote this beta gamma as sine hyperbolic phi, clear? So now what I need actually? Half angle formula, is it? So I need half angle formula. Now this will be the home assignment for you people to show that for, if I have to write cos hyperbolic phi by 2, it is something root of, okay, it will be gamma plus 1 by 2, and if I have to write sine hyperbolic phi by 2, okay, so it will be root of gamma minus 1 by 2. So you know what is the formula for this cos hyperbolic? If I have to write it in terms of half angles, what is cos 2 theta equal to? What is cos 2 theta equal to? 1 plus?
1 plus.
Huh? Just tell me. Okay, what is 1 plus cos of 2 theta equal to? twice cos square theta. Is it? So if I am having instead of theta now theta, it will be theta by 2. So just use those kind of formulas, you will be getting. Okay, just use double angle formulas. Double angle is written in terms of the this half angles. Clear? So there is you should know this. This is a very trivial thing. Okay, so now let's write this very objective. So therefore you are having phi r p. So what is this cos hyperbolic phi by 2? Root of gamma plus 1 divided by 2 plus this is sigma dot n. So this is root of gamma minus 1 n by 2 phi r of 0. Clear? So let's call this as first. Okay. Okay. So now anybody? So in terms of the energy, I always write this thing. Anybody? M c square gamma, where m is the rest mass of the particle. Is this the formula for the energy? Now what is, okay, since c is equal to 1, what is gamma equal to? E by m. Clear? So what this will be equal to? So it will be simply E plus m divided by 2m root plus sigma dot n root of E minus m divided by 2m phi r of 0. So I should call this as 1. Okay, so let's not give the numbering. Huh? Okay. So now what to do? Anybody? Okay, so now what I will do, I will rationalize it. I will multiply this by E plus m in the numerator as well as in the denominator. Clear? And similarly, I will multiply this to make the denominator same. Huh? Okay, since there is an arbitrary unit vector, clear? N is a unit vector. I need to resolve what this unit vector is. Clear? So for that matter, you will see, actually if I rationalize, look here, if I rationalize this very objective, so let's multiply it by E plus m by E plus m. Clear? What it will be? E square minus m square, that's equal to p square. So p square root will be simply the magnitude of the momentum. And multiply it by what? A unit vector. What it will give me? Unit vector, sorry, it will give me momentum vector. Clear? So that means this will be sigma dot p. That is very easy to evaluate. So, samajh aaya? Okay. So let's write it. So it will be simply root of, so I multiply. So it will be like this thing, E plus m divided by root of twice m into E plus m. Clear? So the first term, then plus sigma dot n. So it will be like, right? It is E square minus m square divided by twice m E plus m. Okay, phi r 0. So what is in the denominator? So in the numerator, I am having E plus m plus sigma dot n. So it will be p, magnitude of the p divided by twice m E plus m root. Okay, phi r 0. Clear? So what I have used it here? E square minus m square is equal to p square. Now use vector p is equal to unit vector n times this p. Okay, so what that will be? So therefore this phi r p, so let me write the momentum. So it is E plus m plus sigma dot p vector. So it is sigma dot p vector divided by root of 2m E plus m, okay, phi r 0. So let's call this as 1. Clear? Samajh aaya? So now let's look at the phi L. Okay. So we can write now similarly this phi L P. So that will be equal to, anybody? E raised power. Now here there will be actually minus sigma dot phi by 2 phi L of 0. Instead of plus, what it will be? Minus. You put theta equal to 0 in that formula. So what you will get? So there was actually theta plus I phi. I is sitting outside. So I multiplied by I will give you minus sign. So what it will be simply cos hyperbolic phi by 2 minus sigma dot n sine hyperbolic phi by 2, okay, phi L0. Okay, so that is simply using the same formula, only what is changing? The sign is changing. Everything is same, so that means this sign is changing. So what I will be getting? So, or I can write this phi LP, so that's equal to E plus M minus sigma dot P divided by root of, so I am not putting any vector notation on this sigma, it is understood to be an operator, E plus M, okay, phi L of 0. So let's call this as second. Okay? Now what I told you, at rest, okay, so this phi L of 0 is same as what? Phi R of 0. So we cannot distinguish between the two at rest. Samajh hua? Because spin is not defined at rest simply. Samajh hua? Okay. So therefore, if I am having this kind of situation, so now let's write. So therefore, I can write this phi R of P simply as E plus M plus sigma dot P divided by root of twice M E plus M, okay, phi L of 0. So what I have done? I have replaced this phi R of 0 by what? Phi L of 0, because they are same at rest. So phi R of 0, it is the Sipner at rest, phi L of 0 is Sipner at rest. Clear? So that means they are the same thing, so I can replace it. Clear? So now let's use, okay, so this is equal to E plus M plus sigma dot P divided by root of twice M E plus M. Okay, so phi L of 0 I can write from equation second in terms of phi L of P, is it? So since, okay, so you can write it in which way? So let's write this phi L of 0. Sir. So I will write it as root of twice M E plus M divided by, why it is why I can do this thing? Because if you see in the numerator there is a sigma. Is it? Sigma is a 2 by 2 matrix. That means it's a matrix equation still. So it's a 2 by 2 matrix here. And it is, you have to put an identity matrix here. So, samajh aawa? Clear? What I am doing? I am simply inverting this matrix there. When I can do that? So you can only take these factors on this very side, provided this is invertible, this very side. So and it is invertible. Because you are having, there is an inverse. There is no way you can make this to be 0. So samajh aawa? Why it is not invertible? Okay? So samajh aawa? Just try, give it a try. So what is sigma dot P? It will be sigma x px plus sigma y py plus sigma z pz. What is that? So this sigma dot P will be like this thing. If you remember, it will be simply, anybody? It will be something pz, px plus, sorry, minus I py, px plus I, py and minus pz kind of thing. So samajh aawa? So this sigma dot P will be like, it's a matrix, and this is a matrix with, so it will be simply a matrix E plus M 0 0 E plus M, because it's an identity matrix. So samajh aawa? Okay, identity plus this thing, it's invertible, because the determinant of this is non-zero, determinant of this is non-zero. The determinant difference between is also non-zero. That's why you can invert this thing. So maybe you can raise the question, because this is an operator on this side, this is a matrix on this side, how you are taking it on the other hand side. So samajh, it should be invertible. Clear? So you should be very careful. I can do it. Okay. So sigma dot P. So let's write it as phi L of P. Clear? So this factor goes. Now what I will do is to free this very objective from this sigma dot P, I will rationalize it. So what I will write? So I will put as E plus M plus sigma dot P. Let's write it here. So it is A minus B. Okay, so I should multiply it by A plus B. So what I will do, so it's like this thing, E plus M minus sigma dot P. So I multiply it as E plus M plus sigma dot P divided by E plus M plus sigma dot P phi L P. Clear? Okay. So what this is? So it is E plus M. So let's write E plus M. So what that is? So it is E square plus twice ME plus M square. Then it's plus sigma dot P square into sigma dot P. Then anybody? Plus twice E plus M divided by. So it is A plus B into A minus B. It is E plus M square minus sigma dot P into sigma dot P. Clear? So it's phi L. Okay? Got it? So it is simply the rationalization of the two. Okay, so now what is sigma dot P into sigma dot P? Last time I have told you. So you are having sigma dot A into sigma dot B. What is that equal to? A dot B plus I epsilon I j k sigma dot A cross B. Is that true? So this is the formula last time we have derived. Okay, so now A and B are same. This cross product will go. So it will be sigma dot A into sigma dot A. So what is that equal to? Simply A square. So this very object, this will be equal to P square. And that is equal to E square minus M square. Tisha? Okay. So this M square and this M square goes. Okay. So now let's look at this thing. So this object is what? E square plus M square plus twice ME. Okay, so and it will be minus P square. Okay, what is M square minus P square? That's simply E square. Huh? So you will be having simply twice E. Okay, so this gives me twice E square plus twice ME. So now let's take twice E common. So what it is? E plus 2M. Okay, got it? So sorry, E plus M. Now in the numerator you will also be having twice E plus M. How? So it's E square and E square, twice E square. So twice E you take out, it is E plus M and E plus M, is it? So you take it out. Can you do it? So some of you are just taking out the factors. So and then cancel it with this thing. So therefore I can write this thing phi r of P. Okay. So that's equal to what will be there? Just tell me. So it will be E plus M, okay, plus sigma dot P divided by E plus M phi L. Okay? So is there any root? No. So it will be actually M, only M here. Yes. E plus M is cancelling. So what it should be? Not E, it should be actually M. Twice M square. Yes. What is E square minus P square? That is E square minus P square is what? M square. Okay, so it is twice M square. The same goes above. Huh? So you have to take 2M out. So E plus M. So it will be simply twice M here. So let me check these factors. So it will be simply E plus sigma dot P. Clear? So similarly what you can do, so that will be the home assignment. So you have to do the same thing. Start with phi L P. Okay? So start with this very formula. So for this phi L of 0, what you will write? Phi R of 0. And write phi R of 0 in terms of what? Phi R of P. Clear? So what you will get? Simply phi L of P. So this is the relation. So it is E minus sigma dot P divided by 2M. So now look here. The two are dependent on each other. Clear? So they are related to. So phi R is dependent on what? Phi L, and phi L is dependent on Now let's try to figure out what this transformation is. Let's rewrite it. So you'll see if somebody's, a smart person should recognize it once what it is. It's actually the Dirac equation. Okay? So let's rewrite it. Okay, so let's take the first one. Okay, so let's take the first one. I will write the first one like this. Twice m phi r of p, okay, minus like this thing, e plus sigma dot p, clear, phi l of p, that's equal to 0. And the second I can write like this way, e minus sigma dot p, okay, phi r of p, okay, then minus twice m phi l of p, okay, so that's equal to 0. Got it? So now let's write. So I can write it in the matrix form. So it is twice m. So yes, minus e plus sigma dot p, and then you are having e minus sigma dot p minus 2m. So what you are having here? Phi r of p, phi l of p. So that's equal to 0. Okay? So now let me clear? So it is not 2, I have written 2m, so it's not 2m, it's m. That's I was a little bit worried here. It's not 2m, it's m. I'm sorry. It's m. Just check it, so it's m. Okay? Huh? Clear? Okay, so can you identify it as a Dirac equation? Huh? So let me write this way. So let me define now the matrix. So let me write it in the proper format. So let's define this. So how much is time? Phi of p. So you are having phi r of p. Okay? Phi l of p. So this will give you actually the interpretation for the separates for particles and antiparticles. Clear? So you'll see actually the Dirac equation is a relation between the two. So it connects the two types of particles. Okay? So let me define this way, and let's define gamma 0 is equal to 0, 1, 1, 0. Okay? So let me define this kind of matrix, and then gamma I is equal to 0, sigma I 0. Okay, so this is the definition of this. So I should put a minus here. Okay, so if I am defining my gamma matrices like this way, so let's define them in this way. Then I can rewrite this very equation. Clear? So shall I leave it to you? So you will show. Okay, so you will get it like this thing. Gamma 0 p 0. Okay, I am defining p 0 is defined as E. So it is simply P0 plus sigma dot P, clear? So you will be simply getting like this in gamma I, Pi acting on this, minus M or plus M, or minus M, yes, minus M acting on this psi of P, that's equal to 0. So what this is? It is gamma mu P mu minus m acting on psi of p. What is that equal to? 0. So what this is? It is your Dirac equation. So that means you have got the interpretation of Dirac equation. It connects the two types of signals, okay, which are related by Lorentz group, okay, extended by parity. So samajh aawa? Now let's take mass equal to 0. So that is last point. Okay, if I take mass equal to 0, so you can look it from here. Special case quickly. So let's take m equal to 0. So what happens? So you will be having, so simply what? It is P0. Okay, so it is simply, okay, E plus sigma dot P, okay, acting on phi L of P, that's equal to 0, and you are having E minus sigma dot P acting on what? Phi r of P, that's equal to 0. Okay? So since this is equal to 0, you will get two independent equations. Clear? So when the mass of the particle becomes 0, so what you get? Two independent particles. Clear? So samajh Shaman? You got my point. So that means they are not connected to each other. So they are independent of each other. This phi r, so you will get actually the interpretation of this phi r here. Eh? So you get actually two types of particles. Eh? Okay, one moving with one governed by this equation, one governed by, we call this equation we call it the Weyl equations. Okay, so let's interpret these things, what exactly it means. So let's take this one. So you are having sigma dot P acting on this phi r of P, so that's equal to simply E phi r of P. Clear? So what is mass here? Mass is 0. So what is the energy then? So energy in this case is simply P. Because mass is equal to 0, what will be the energy? P. Samajh Shaman? Or in other words, this P naught is equal to E, that will be simply P. Clear? So samajh Shaman? So I can write this sigma dot P like this thing. Sigma dot P I can write like this thing. P multiplied by this magnitude of P. Can I write it? P is the magnitude of the momentum and you write a unit vector. Clear? So what is sigma dot P? Okay, so let's write it. So it will be simply sigma dot P phi r of P, okay, is equal to plus 1. Okay, phi r of P. Clear? Because now what I have written, E is equal to P, is it? So then you divide this. So you write this P in terms of this P. P and P will cancel. Is it? What remains here? Plus 1. Now let's give the interpretation of the sigma dot P. What is sigma? Sigma simply gives you the spin of the particle. What is unit vector P? It gives you the direction of the momentum. Clear? So that means you are projecting the spin along the direction of the momentum. What it represents? It gives you the helicity of the particle. Clear? So that means this is simply the projection operator for the helicity. So that means this particle is having a helicity of how much? Half. Okay? So it's, sorry, not half, plus 1. Plus 1 helicity. Clear? Now if I look at this very equation, so let's look at this very equation. What you will get? You will get actually sigma dot P phi L of P is equal to minus E phi L of P. So what you get actually? So or you can write in the same fashion, sigma dot P phi L of P you will get as a minus 1 phi L of P. Clear? So that means you are getting a helicity of how much? Minus 1. So that these two particles are entirely different of I mean they are not the same particle, is it? So either you can find if you are having a massless particle, okay, spin half massless particle. We are not considering the spin one massless particle, that is photon. We are just considering the spin half massless particle. So what you have discovered here? So you will be having a particle either having the positive helicity or having the same particle does not have the same helicities. I mean sorry, both helicities. Clear? So we call one as the right-handed particle or the left-handed particle. So think of the neutrinos. You will learn it in the particle physics. So neutrinos, neutrinos or antineutrinos, these are the kind of particles having the almost mass is equal to 0. Clear? But they are having the spin half particle. Okay? So they are being found in nature either the right-handed particle or the left-handed particle. You cannot find the same kind of particle in the both states. I mean right-handed or. So this is a kind of breakdown of the symmetry. You can either have what? Left-handed particles or you cannot have one particle having the same handednesses. Okay? You cannot figure out the, let's say neutrino. Let's assume one particle is having right-handed and it's another. It is antiparticle is let's say you are having particle A. Its antiparticle is particle B. Clear? If my particle is right-handed, I can always find out its antiparticle as the left-handed. Clear? I cannot find the particle and its antiparticle in the same kind of states. Clear? So this should now give you the clarification why I have used what? this phi r and phi l. So you are having two-handednesses, left-handed signals as well as right-handed signals. Clear? So this finishes, I mean, our introduction to this Lorentz group. So you should now understand what. Okay, so there is one take-home lesson. Why Dirac matrices have to be four-dimensional? So we have given one argument that first argument that since we require in our representation, so in the four-dimensional Minkowski space-time, so sigma x, sigma y, sigma z, they are not sufficient to describe the Clifford algebra, is it? But as a more general interpretation, what we have figured out, this Dirac, why they have to be four-dimensional, these matrices have to be four-dimensional in the four-dimensional Minkowski space-time. Why? What is the reason? Because Lorentz group extended by parity allows us to connect the different kinds of signals via Dirac equation. Clear? That is why we require the four-dimensional representation of the Dirac matrices. Clear? Samajh aaga? Okay, so that's all.